and then we'll wait for a few minutes. Unfortunately, we moved recently out of our normal offices because of a building issue that needed to be done. So we're sharing offices in like some part of the building that I've never been to before. So it's an interesting.
Completely understand. And you're down in Arizona, correct?
Yeah.
You're on site at. Okay,
yeah.
That's what I thought.
But so the other thing I will tell you is that the project, the Event Horizon Telescope has 300 people, and what we find is because of time differences and this and that, usually there are not many attendees real time, but the recordings, and again we can have the recording completely internal to our project members without any access to the outside world, and typically people watch it after the fact. So
wait, just to confirm, so you said that when you do share the recording, it's only to your members?
Only to the members will be just like the people that would be allowed to call in today, like password protected. But when what I was asking you is to make it widely open.
Okay, that's what I thought you were asking. So I just want to make sure I understood. So I get the correct, because if it was just shared to your members, then that probably wouldn't be an issue at all.
People in the project can have access to all the password protected. So that's probably most people what they're going to do. I see already Angelo coming in. We'll wait for a couple more minutes and then we'll start.
Excellent.
It is 11 a.m. Arizona time, and people are signing in. So let's wait for a few more minutes before we start.
Sounds good. No worries.
I will give it 1 more minute and then we can start, as people are slowly joining in.
Sounds good.
Okay, let's start. Welcome everybody to this month's Black Hole PIRE webinar talk, I presume, Black Hole PIRE webinar. My name is Dimitris Psaltis. I'm a professor of physics and astronomy at the University of Arizona, and I will be hosting the webinar today. As you know, this is one of many webinars that we're hosting as part of the National Science Foundation funded Black Hole PIRE project, which is one of the projects part of the bigger collaboration, the Event Horizon Telescope collaboration. And all the past webinars have been recorded, and you can find them in the YouTube Black Hole PIRE Science channel. And if you want to have a look at the upcoming webinars, you should go to bhpire.arizona.edu, where you will find the list, I think, of all the webinars all the way to the end of this academic year. Today's webinar will last about an hour, including time for questions. And as with all other webinars, your feedback will be very important to us. So at the very end, there will be a very short survey that we would ask you to complete. The way that the webinar works is that most of the attendees do not have access to be able to immediately give questions, but we would like to make our webinar quite interactive. So if you have any questions during the talk, please put it on the chat on the right, and I will be monitoring them. And if it is a short question or a short thing that needs to be answered, I will give it to our speaker. If it's a longer question, then I will open the possibility for an attendee to ask the question directly. And at the very end of the webinar, we will have a more open Q&A time for everybody to talk about. Having said that, we're planning to have this webinar to last about an hour for the including Q&As. And at the very end, again, one quick reminder I will give you to fill the survey for our webinars in our project. So this is all I have to say about little housekeeping things to cover. And before spending any more time, let me introduce today's speaker. We're very happy to have with us Aaron Booker, an HPC specialist from Amazon Web Services. I understand that Aaron worked at the University of Minnesota until 2016, where he did enterprise architecture and technology planning for the 5 campuses of the universities. And since then, he has moved to Amazon Web Services, being an HPC specialist, concentrating on architecting and optimizing HPC environments for public sector customers. The presentation he's going to give us today is titled Accelerating Your Research with AWS. So thank you very much, Aaron. It's wonderful to have you here. Please go ahead.
Thank you. I appreciate the introduction. So yeah, today I want to talk about accelerating research with Amazon Web Services. And what I was thinking what we're going to cover today is we're going to first talk about just some fundamental concepts of like running your research workloads on top of AWS. Then we'll move into actually looking at some of our specific HPC capabilities of the platform. And then we'll talk about how you can actually further your research dollars by using our spare compute capacity on top of AWS for your research. And then I'll wrap up with how you can actually get started and some resources that we have available for you. So with that, let's first start out about just some concepts when you're thinking about running research workloads on top of AWS. And so first is, if you look at a comparison to how you do research and how research is done in the past, a lot of that research is done with on-premises clusters. And so with those on-premises clusters, you have a fixed set of capacity that you're working with, and generally just a few different node types that you have to work with. So you might have a lot of general compute, but then you may only have access to certain limited large memory systems, or you may have a system with a GPU. And so that really kind of forces you to use that capacity to cram your workloads on top of it, and it causes you to kind of use that capacity inefficiently. When in reality, if you look at how research works and the different jobs that you have to run, is that you do have surges that you need to handle. And a lot of times with certain applications, some actually will work better with larger memory, different kind of compute, or they could use GPUs, and you might not have all of that available on premise. So really what you're doing is you're trying to burst into different kind of workloads that ultimately causes you to wait in a longer queue on premises when you're trying to get those same resources. So when we think about it on top of AWS, it's really about shifting your way of thinking and less about cramming everything to how you've done, but also now focusing on to how can you use the resources when you need them. And there's a couple different concepts that we think about when you're trying to build your clusters on top of AWS. So first, when we think about our infrastructure, it's rather not forcing your applications onto a single cluster, but it's really now about building clusters for your specific applications. So if you have an application that needs a bunch of cores that you need to run on, you can run that. If you have an application that runs on large memory, you can actually run that in parallel at the same time. And there's also another concept too, when I like to think about how clusters work on top of AWS, is that you can now, instead of having a single cluster that you're working with, you can actually run concurrent clusters on top of AWS. So let's say if you had to do 10 like serial runs of an application of 10 different cases, you can actually do that all at once on top of AWS because each application could have their own cluster. A second thing to think about too is the collaboration that's enabled when you're working with cloud computing. So I remember the days when we used to ship hard drives around for sharing data sets. On top of AWS, it kind of shifts your way of thinking now, where now you can actually host a data set and you can securely share it with your collaborators on top of AWS. And so what I mean by that is that the data can stay stored, and then people can bring their compute to where that data lives. You're no longer transferring that data back and forth, and you can do this on an individual basis with your collaborators, so you're not just opening this up to the world. And the final thing to think about is the flexible configuration options that you can do as well on top of the platform. And what I mean by this is that you can experiment when new instances are launched. Those are virtual servers. When Intel releases new hardware, we introduce new virtual servers, and you can upgrade whenever those become available. You're no longer making a commitment to something for about 5 or 6 years before you're going to upgrade that hardware. And you can also test different workloads on different configurations of those virtual servers rather than buying a physical box that you're going to put inside your data center. And when we look at the infrastructure on top of AWS, we don't need to understand this in deep detail, but our infrastructure is broken out into what we call regions across the world. And inside of those regions, there's a concept that we call availability zones where our infrastructure is. And inside of those availability zones, the important thing to understand is that the region is designed in such a way that those availability zones are on like separate floodplains, different fault lines, so that if there ever is a natural disaster, it's designed to not take out the entire region. And we do this in such a way so that as you're saving, let's say, data into the region and you're selecting a storage service, it'll be more resilient to failure, so that you can store your data in such a way that it's more durable. And the other important thing too about our regions is that if you have, for some reason, compliance needs, when you upload your data inside of, like, let's say, a region like Oregon to our object storage S3, that storage is replicated within the region, but it does not leave the region. So if you have compliance requirements that it has to stay inside of a certain country or something like that, we can help meet those needs for you as well by the way our infrastructure is designed. And when running on this infrastructure, when it comes to HPC, we really kind of break it into a couple different cases from a workload perspective. And so if we look at first, we break it into like tightly coupled workloads. So these would be your MPI-based jobs. So a lot of times this might be weather forecasting, computational fluid dynamics, seismic work as well. And then we also have loosely coupled workloads. So these are the more embarrassingly parallel workloads that we can talk about. And so a lot of times this might be Monte Carlo simulations that we see our customers doing, or even some of the genomics work that they do. Of course, if you have accelerated computing, we can help you meet those needs as well. So these are workloads that might take advantage of either GPUs or even FPGAs. We have resources available for you that we can talk about a little bit later. And then we also have, a lot of times in workloads, a visualization component. So if you look at like the post-processing of like a computational fluid dynamics case or something like that, we do have some services available as well that we'll walk through. And then of course, if you have any kind of AI or ML or even distributed machine learning, we see that work a lot with our customers as well. And then of course, there's also high volume in data analytics. And so this might be like satellite imagery or something like that as well from a high volume data perspective. But I think it'd be also good to show you just what some other people are doing on top of the platform as well before we start going into the technical capabilities as well. So first, I want to talk about is, this is a case study from the University of California, Santa Cruz, where they did their genomics analysis on top of our virtual infrastructure. And what's unique about them is that they were forecasting that this was going to take about 3 months for them to do. And when they leveraged AWS, and specifically they leveraged our spare capacity that I'm going to talk about how to access later on, they were actually to bring this in from 3 months to less than 4 days for all of their processing. So this was 20,000 RNA sequencing samples that they were doing. They did it in less than 4 days. They did this on about 32,000 cores on top of the platform on their spare capacity. And originally what they were doing, if they were going to stand it up, it was going to be about $800,000 for them to do it. And they did it all for about $26,000 on top of the platform in that less than 3 days. And then they were able just to turn off that infrastructure so they no longer needed it. Another example would be the Australian Museum Research Institute. And so they did another genomics processing, and they did 3.2 billion base pairs that they were processing. And they were leveraging that concept of concurrent clusters on demand. And so what they were doing is they were concurrently running about 500 to 1,000 core clusters, all simultaneously doing this processing on top of our platform as well. And they were also using the spare capacity that we talked about. From a tightly coupled perspective, so we can talk about what San Diego Supercomputing did. And so they were doing a seismic simulation on top of us. And so they ran a tightly coupled workload with MPI on 768 of our virtual servers. And this gave them about 27,000 cores that they were running on. And they did this also on our spare capacity. And they did this actually for research that they did for the International Supercomputing Conference that just happened this past summer as well. So I'll pause there just from a running workload capability. Now we can start to dig into the technical details unless there's any questions.
I have not seen any question yet, but I had a quick one
Yes.
from the last use case that you gave, Aaron. It was the San Diego Supercomputing Center. Was there any reason why they have their own in-house clusters, in-house supercomputers? What was the benefit of moving to the Amazon Web Services?
So it was, part of it was getting capacity so they could do research on their algorithm that they were doing. And that was part of the research that they wanted to do on cloud computing. So they did it of a comparison for doing their edge algorithm on top of AWS and on top of Google as well. And then in comparison to what they were doing on premises. And so they were showing kind of what the comparison was across the different providers and how that compares to the capability of on-prem.
Is this something that's publicly available, the outcome?
It is publicly available, yes. And I can follow up with the link. It's
something at the bottom, I say.
Yeah, there is. If you want, I can also send it to you. Otherwise, it's in the screenshot we can do as well.
Thank you very much.
Yep. So let's start digging into some of the technical capabilities of the platform. And we're not going to go through everything, but really what I want to highlight on is things that I see a lot of people from an HPC perspective using on top of the platform. And so really when we start looking at HPC components, we break them up into about 5 different categories. So there's, at the heart of it, there's compute. And then of course we have storage, and then we have the networking as well. And then there is the visualization component that I said that a lot of times happens in like a post-processing of results. And then ultimately there's also another component of it that we frame as like automation and orchestration. And so this is really what you surround all of these these components with to make it so that it's easy to use. So how do you launch all of your resources? How do you coordinate the storage and the compute and different services like that? That's what we really consider with the automation and orchestration. And first, what I want to start out is talking about our compute. And so our virtual servers run on top of a service we call EC2. And we call these EC2 virtual servers instances. And so as you can see, we have over 200 different instance types to choose from, which may sound daunting at the beginning. But when you start to look at HPC, you can really start to whittle this list down because only certain ones are probably going to be attractive for HPC workloads. And we break these different instance types into what we call instance families or categories, you could call them. And really what this is kind of grouping them together based on kind of what's the underlying hardware and then also what you might use them for. So a lot of times we might see people that are doing like CFD or computational fluid dynamics use compute intensive instances. Sometimes a workload may require more memory, so they might use like a memory intensive instance or a general purpose instance. And then of course, like I said, there's also accelerated computing where you might need something like a GPU or an FPGA. And so when you launch your instance, that's your virtual server, and that's what's going to determine what the different capabilities of that instance is. And so it'll determine what the underlying processor is, how much memory does it have, things of that nature. Does it have local storage, or is it using a storage service? That's all decided when you choose what instance type you're running on. And like I said, with HPC workloads, it's generally fairly easy to choose what kind of instances you want, because there's a limited selection that you're probably going to use. So like from a tightly coupled workload perspective, you're going to be running on the largest instance size inside of the family, just because it makes sense to run on with most compute local before you start crossing the network for your calculation, like the FBI or something like that, for example. And then specifically for EC2 instances, I do want to highlight a couple that we see a lot of times used for high performance computing. And so the first one I want to talk about is what we call our C5N instances. And so just from a little bit of background on how these things are named, is that the C stands for like what family you're in. So in this case, it's going to be the compute optimized family. 5 is what generation of that family you're running in. And so like there's a C4 and this is a C5. And so the C5 is newer than the C4, et cetera. And so eventually someday we may launch a C6, but you can see kind of how those generations build. And then in this case, the N is the N variant of this. And so this means it's optimized for the network. And really what that gives you is two different capabilities here. The first is you get 100 gigs networking bandwidth attached to it. And then the second part that I'm going to talk about in just a little bit is you also get the capability to use our elastic fabric adapter that I'll go into more detail about, which is targeted at MPI-based workloads. And so with the C5N, in this case, if you were wanting to use EFA, you'd be running on the largest instance type. So if you wanted to do multiple instances for your MPI calculation, you would just do multiple instances, the largest family or the largest size. And then also the C5N, in this case, they're running on custom Intel processors that we have built for us that are based on Skylake. So it's no different from the Skylake architecture. It's just that we have custom processors made from Intel to use in our side of our data centers. And so a lot of times people ask about how will their software work on top of AWS? Can they use Intel compilers? And yes, we do recommend using Intel compilers, and you can recompile your software if you want to, but just to know that you still are running on an Intel processor at the end of the day for these C5N instances. A second instance type that I want to talk about is an accelerated instance type. And so this would be really targeted more for distributed machine learning if you want to do something like that, or if you needed multiple GPUs inside of a single instance. So what the P3DN has on it is, so once again, P is just the family. So that's our GPU, one of our GPU families. And then the 3 is the generation. And then N, like we just talked about with the C5N, is for the network variant of it. And then with the D, it actually means that it has local SSDs attached to it as well, rather than using like a storage service for block storage. So basically what's giving you is the capability to have a local scratch space, like a ephemeral disk that you sit there that you can load in your data set for. And so with the P3DN, one of the features is it has the 100 gig networking, the ability to use EFA, but then it also has 8 NVIDIA V100s in it, the 32 gig memory variant of those that you can use on each instance that you launch for the P3DNs as well. So we really see a lot of people trying to take advantage of this for distributed machine learning like I was talking about. So I want to talk a little bit about EFA, especially when it comes targeted at tightly coupled applications and MPI-based workloads. So we talked about two instance types, the C5N and the P3DN. And I said that it gives you the capability not only to have 100 gigs of bandwidth, but also to use what we call our elastic fabric adapter, or EFA. And essentially what this is a technique that's very familiar to HPC users of OS bypass. So you're no longer using the TCP IP stack. And so now you can take advantage of EFA on top of our platform as well. We have it on more instances than just the C5N and P3DN. We've actually recently just announced that it's now available on the M5N and the R5N. And essentially is just from a guidance point of view of what you're doing when you're going from the C's to the M's to the R's, is really what you're looking at is what is the memory per core that you're using. And so as a rough guideline, like the C5N has about 5 gigs of memory per core, the M5N has about 8 gigs of memory per core, and then the R5N has 16 gigs of memory per core. So this really goes back to that idea of you can really build a cluster for your particular application that you're trying to run. So you might have a stage of your workflow that needs more memory, and so you could choose for that stage, like the M5s or the R5s. And then if you have a more computational intensive part of your workload, you could then just choose like the C5N if you don't need that extra memory. Because with cloud computing, what it really comes back to is pay for only what you use. There's no reason to have unused resources running and that you're paying for. So if you can use less memory per core, then choose a different instance type that has less memory per core, rather than just having running on R5s every single, like all the time, which would be more expensive than running on like C5s. So with EFA, like I said, it's really targeted at the MPI-based applications with an OS bypass feature. And what that looks like is that if you look at like kind of the software stack might look like without EFA, is you typically have an application, an MPI implementation. This would be like OpenMPI or Intel MPI. And then that talks to the TCP IP stack that then talks to the driver that then talks to what we call our elastic network adapter device, or certainly would be like a NIC inside of like an on-premises server or something like that. So with EFA, you're still going through a software stack, you still have your application, you still have an MPI implementation like Intel MPI or OpenMPI, and then you're using libfabric essentially to talk to the EFA device as well. And so if we look at how things compare with EFA versus not EFA, is that this would be an example of a computational fluid dynamics case that ran on a 140 million cell case of a Formula One race car. And so what the graph is showing on the left-hand side is that it's a comparison between running this case on C5N with EFA compared to running on a Cray XC50 that would be on premises at some people's sites. And as you can see that the C5N example is actually tracking better than the Cray, up to about 2,400 cores or so. And then it's maintaining along with the Cray up to about, I would say about 4,200 cores in this example. And so this really starts to show you that with some of the technology advances, how it compares to other traditional HPC resources. Another example to look at too is if you look at how another CFD case, which is an MPI-based workload, compared to what we had before EFA and now compared to with EFA. And so this is another CFD case, like I was saying, and the red line would be what we call ideal scaling. And then you can see that the purple line would be what we had without EFA. So just using our elastic network adapter running the same case. And you can really see it starts to fall off right after that 400 core mark. However, when we start running the same case with EFA, you can see that it's tracking much closer to ideal scaling and much further than what it was doing without EFA. So this just kind of shows you an example of how different technologies can work when you're trying to look at what you might use to run your MPI-based workloads. So that's really what it has to do with kind of compute and networking and how that kind of all ties together from a high-level overview from an HPC perspective. But now I want to talk a little bit about storage as well. So if we look at, we'll first talk about kind of some general storage options, kind of what we see used across our customers, and then I'll also talk about a storage service that we have targeted at high performance computing as well. So we do have a variety of different storage options you can choose from. I already talked about that some of our instances or our virtual servers have the ability to have local storage inside of them if you needed like a local SSD for a scratch based. Otherwise, what you're doing is you'll be running on our block storage service, which we call Amazon EBS or Elastic Block Storage. And so really what this is about, just like having like adding another hard drive inside of your computer or something like that. However, it's a managed service that we provide. And so this would be the block storage service is something that like you'd be booting off of for like your root directory and things like that. But then you can also add multiple volumes, and volumes are different types as well to your instance when it's running. We also have shared file storage from managed file storage service. And so this is what we call our Elastic File System. And this is basically a managed NFS share that you can mount on your virtual servers that is very much similar to like what a NAS might look like on your on-premises systems. From an HPC perspective, Amazon EFS really works well for things like home directories. And then I'll talk about another storage service that you can look at if you're looking for more of a high performance storage service. But the nice thing about Amazon EFS is that as you store more files inside of it, it grows with your files. And so you're not really provisioning storage with it. You're just paying for what you use when you use EFS. And when you use less space, it actually shrinks the file system as well for your bill as well. And then the third piece of storage I want to talk about is Amazon S3. This is our object storage. And so when I start talking with a lot of researchers, object storage might be something that might be a little bit new to them. Just because it's the way you interface with it is not necessarily something that you would mount like you would with a file system. And really you're interfacing with object storage programmatically. Object storage is a very scalable storage solution for us. And it's also a very cost-effective solution for you. And so really, when I start to work with researchers, it's about how can they get used to object storage, because you can interact with it. You don't have to use, like, let's say, a Python API to interact with it. You can use a command line utility and things like that. Is getting them to look at object storage as really kind of more of their long-term durable data storage for their work, for their different results and for their input files and things like that. And really, once they start using that, they can start to decouple their storage from their compute and from the rest of their solution, and so that they can have a more cost-effective solution overall as well. So if you think about it, if you're now leveraging S3 for your data store and then moving data from either S3 into EC2 when you need it, you're no longer paying for those compute resources to be running. If just to store your data, you're actually just using S3 for it as well. And so when we look at high performance computing in particular, I do want to talk about basically our managed Lustre service that we have available. And so this is a service called FSx for Lustre. We released it about a year ago now. And really what it is a managed Lustre service that you can use. And so if you need a high performance file system, previously what you would have to do is launch a number of EC2 instances that then you would be managing that file system yourself for. Now we have a managed offering called FSx for Lustre, so you no longer have to do that. So it really reduces that pain of managing a parallel file system inside of AWS. There's also some really nice capabilities that FSx for Lustre brings as well. And so one of the things that I really like to talk about is how FSx for Lustre can actually be linked to an S3 bucket when you actually create the file system. And what I mean by this is that you can have your data sitting inside of S3. So for example, let's say you had a petabyte of data sitting inside of S3, but then only for your processing, you only needed, let's say, 9 terabytes of that data. You can create a file system with FSx, link it to your S3 bucket. When you create that file system, it'll actually load in all of the metadata from S3. And so you'll be presented, when you mount that Lustre file system, you'll be presented with a file system that looks like it has a petabyte of data inside of it. And then when you access the files for the first time, FSx for Lustre actually manages the transfer from S3 into the Lustre file system, where then you can do your processing. And so when you first access the files, it'll pull them in as needed. And then also when you're doing your processing, and then if you save your data, let's say to the FSx file system, you can then actually call a command that'll archive that data back to S3 and then allow you to deprovision that Lustre file systems. So it really goes back to that idea of only paying for what you use when you need it. With this model, we really look at kind of like the Lustre file system. I would compare it to something like Scratchbase on premises, where you're really using it only temporarily, where you're really pairing it with a long-term data store like S3. But it really creates a more cost-effective solution so that you're no longer paying for, let's say, a full petabyte of Lustre if you don't really need it to have all of that in Lustre at the same time for accessing. So far we've talked about compute, and we've talked about networking, and we've talked about storage. Now what I want to talk about a little bit is some of the services that we have that are available for orchestrating your workloads and orchestrating those underlying components to create a solution for you. I see people do a variety of different things. Everybody does things from sometimes even the simplest, what it would be is they might create their own batch script to launch some instances for their processing for their workload, to they might use a different service that I'll talk about, like AWS Batch, to coordinate their actual infrastructure. They might use something that I'm going to talk about, like called ParallelCluster as well. Or they might even run their own templates. But we do provide a managed service called AWS Batch, which basically what it does is it provides you a queue that you can submit jobs to for batch processing. And then it will spin up, based on your configuration, what EC2 resources you need to process those jobs based on like what requirements you told it to do. And what Batch has done is it's based on a container. And then when you create your job with those containers and you submit jobs, you're saying what the resource requirements are as well. And so as you submit to the queue, Batch will then spin up those resources, process that queue, and then it will actually deprovision those resources as well when they become idle. AWS Batch is actually available for loosely coupled workloads, so embarrassingly parallel workloads, or we actually have it available as well for multi-node parallel jobs or MPI-based workloads too. So you can do both with Batch on top of the platform. Another service that I want to talk about is really an open source tool that we created. It's called AWS ParallelCluster. And what this is that it is open source tool that's a command line based tool that you would install like on your laptop or something, or your desktop or something like that. And then it interfaces with AWS to coordinate the resources that you need. And really what ParallelCluster does is it creates a very familiar environment compared to what people are used to with like on-premises clusters. And so through the automation that ParallelCluster has, it'll create a login server that you can log into. That server will have a scheduler. So it'll either have, based on your configuration, it'll either have SG, Slurm, or Torque. And then it'll have shared directories out to the compute instances as well. And so the way ParallelCluster works is once you have your cluster created, you log into the login node and you submit your jobs. So let's say it's Slurm. ParallelCluster has tooling inside of it that will then start to spin up AWS resources and EC2 instances to process those jobs that are in the queue. And when those instances spin up, they're mounting a common home directory. They have a shared project directory. And so it really is just like you would have with an on-premises cluster, except for that when those instances start to become idle, ParallelCluster then starts to deprovision those compute instances so that you're not paying for idle resources that are running. And so it's kind of a nice way to bridge what would be a lift and shift approach from like your on-premises environment into a cloud native approach. So it's kind of in between. So it gives you some of the benefits of the cloud by basically allowing you to only use resources when you need them and to pay for what you need, but then also still giving you kind of that familiar environment as well. So we see a lot of people start out with AWS ParallelCluster because it's a really quick way to get started, just to test their workloads, and then they either continue to stick with ParallelCluster if it's meeting all of their needs, or they might look at a more customized solution, or they might look at a more cloud native way, such as like AWS Batch, for example, to run their HPC workloads. So I want to pause there because we just talked about some of the actual HPC capabilities and want to see if there's any questions before we go and start talking about how we can use our spare capacity.
I'm monitoring the chat if somebody has some questions, and I think we can continue.
Excellent. So the next part I want to talk about is how do we use our spare compute capacity for your research? And so this is something that has to do with how you pay for resources on top of AWS, and specifically, this is how you pay for EC2 instances. So when we look at purchasing EC2 instances, we have 3 different models currently that I'm going to talk about. And so we have basically what we call on demand. So this is paying for the capacity that you need when you need it. This is, as long as you're using a non-licensed OS version, this is actually per second billing that EC2 uses. And this really is the default way that people start out with. And so it's where you can start in the console or use the command line or API where you just need an instance and you launch an instance. That's by default is billing, what we call on demand. And this is really works well for when people are getting started, and also when people are starting, they might have spiky workloads, they might just need a surge in capacity for a little bit, and they would choose on demand in this case. The second category that we have is what we call reserved instances. And this is really where you're making where you know you have a workload that's running a steady state, and you're making then a commitment to us that's saying you want to run this compute capacity for 1 or 3 years. And with that commitment, we will then give you a discount based off of what the on-demand price is for that instance type. And so then with that commitment, the instance, you're billed for it for the full year. And then you can always just leave it running. And so we see people do reserved instances a lot for if they know they have, like I said, like a steady workload running. Sometimes like in an HPC scenario, they might have, let's say like a login server always running, or a certain amount of compute capacity always running. So they would choose reserved instances in that case. But what I want to talk about is what we call our spot instances, which is EC2 spare capacity that you can use. And with the spare capacity, spot instances, we actually make this available to you with up to 90% off of what the on-demand price is at the time. And this is really good for flexible workloads. If you have fault-tolerant workloads, we see people doing not only like loosely coupled workloads, so if you think of like a Monte Carlo simulation on top of AWS spot capacity, or even tightly coupled workloads like the Seismic workload that SDSC did as well. And really, so with these spot instances, you're using the EC2 spare capacity, like I was saying. And we talked about how that with the price discount at up to 90%, but then also with that discount, the way spot works is that you can launch the spot instances and you're getting the discounted rate. And then if we ever need that capacity to meet another demand, will actually send you a notice before your workload's interrupted, saying that we're going to interrupt the workload to reclaim that capacity for a different purpose. We see a lot of researchers when they use Spot instances, they can actually do, they can run more workloads at once. And so really that accelerates your research and accelerates to your results. And then also AWS Spot instances are actually integrated with a lot of our other services as well. And so this would be things like AWS Batch can take advantage of Spot instances, AWS ParallelCluster can take advantage of Spot instances. So really it's by changing one or two lines in the configuration file for your parallel cluster, you can be running on our spare capacity inside of AWS as well. And like I said, a lot of time when I work with researchers, they start out with on-demand just because it's the easiest way to get started, but then they move as quickly as possible to using Spot instances so they can get more compute capacity for their research dollars that they're working with. And so what this might look like if all three of these models are being used together would be is if you look at what it would be for like a weather forecasting and modeling. So if you had daily forecasts that you were doing every 6 hours, you would be looking at really at doing like reserved capacity for that because you're doing it constantly. It's a steady state workload. If you're doing something like climate modeling, a lot of times we see a lot of people do that on Spot instances. And then if there was ever a weather event that you needed capacity for, that you needed to make a forecast for that was outside of what you had for your reserved capacity, you would possibly use on demand for that, for that part of your forecast. And so this is just kind of a holistic picture of how these three models might work together for a workload. When we talk about spare compute capacity, a lot of people ask me, like, how much is there? Like, can you really do large scale workloads on top of AWS, on top of these Spot instances? And so previously, as an example, I gave what San Diego Supercomputing did, and they did it on about 27,000 cores, a little bit over that, for a single tightly coupled workload. And then here's just another example of Clemson University doing another workload on top of us inside of a single region. This would be in our North Virginia region, and they did a little bit over 1 million virtual CPUs for a single cluster that they were running for a single workload that they were doing. And they did this concurrently as well. And this was done over the weekend. So I'm going to pause there. That's kind of a high-level overview of Spot instances, how you can use them, just an introduction to it. But if there are any questions on Spot, I'm happy to take those as well.
Yeah, one question is, for initial development and testing, is the Spot capability capacity what you would suggest? And if yes, is it possible to just have Spot capabilities without having on-demand or the standard, or do you have to buy something in order to be allowed to use the Spot?
No, so you can use Spot without buying anything else, like without having on-demand instances running or reserved instances. It's available for you to use. Really, all you're doing is when you launch your instances, you're specifying that you're going to launch a Spot instance instead of an on-demand one. So it's really flexible that way. We see a lot of people use it for dev and test. The thing that I would say is any kind of workload that you consider putting on Spot is think about decoupling things in such a way and thinking about your storage so that if your default behavior is to terminate the instance when you get interrupted, you either have a capability of snapshotting that data that's there or that's written into your application where it's taking regular snapshots, or you're using with like external storage or something like that, just so that you want to have that thought process so that you don't lose work. That's because of it. And there are different options to happen when your Spot instance gets interrupted. So for instance, you can have it where instead of having it being terminated, which is the default behavior, you can also have it where the instance is actually just shut down or something like that. But those are just some of the considerations that you should think about when you're looking at Spot instances. But I highly recommend to use them as much as you possibly can for your research. So really think through what your workflow is, how you can adapt it so that you can use that capacity, because now you're getting it for so much less than what it would be from an on-demand price standpoint. And I think, sorry.
No, I was going to say, do you provide any like development or initial development or tryout allocation that somebody can see if this is a worthwhile, investment of their, resources and time?
Yeah, I'll talk a little bit about that too at the end, but we do regularly work with different customers to kind of construct what a POC might be. And so really what that is that when we construct a POC, we'll identify like what should be tested or what the goal of the POC actually is. And then a lot of times we can provide credits as well to accomplish that POC. And really what we're looking at with POCs is kind of what is just to prove out that it will work. Not necessarily here's to fund the entire workload. It's more of to prove the concept that it could run on top of AWS. And really the best steps to working to getting towards a POC with those credits like that is working with the account manager, since they're the ones that provide the credits.
Okay.
But yes, it's something that we regularly do, because especially when you look at like HPC on top of AWS, it's a different paradigm, and there's some different concepts that you're working with. And so if you're new to the platform, we really want to try to help you as much as possible to get used to using it and to make sure that you're successful. And a lot of times I'll even help customers work with their POCs so that it's not like they're starting with a blank page, so that it's trying to reduce that barrier just because there are some new concepts there. And so we don't want to have a poor experience from the beginning, essentially.
Especially for an academic endeavor like our project, and all the funding that we get is in some ways requires that we demonstrate that what we're going to use is worthwhile and workable, and then we go out and get funding to be able to cover the expense of doing on demand or anything else we might be doing.
Right. Yep. And that's exactly something that like we work with regularly with different institutions and different groups if they have something they want to prove out, just to show that they can do it. Mm-hmm. And then knowing that if they do select that option, that then they would fund it from there on.
Yeah. Thank you.
Yep. So the last section that I want to talk about, because we have about 15 minutes left here, is I want to talk about some resources that are available to you to help get started on top of the platform. And so really, when we just think from a high level starting point of like, how do people get started on top of AWS, specifically around HPC and research, where is really you start to look at your workload, your application that you want to run. You determine kind of what kind of compute and storage you need, what kind of networking. So this would be is that you determine how many cores do you want to run on, how much memory do you need for your application, do you need GPUs, things like that. And then based on that, researchers, like I said, one of the easiest ways for them to get started in an environment is to create a configuration for ParallelCluster, which provides kind of that traditional on-premises environment for you inside of AWS. And then once that's created and your cluster is stood up, then you just log in, submit your jobs. A lot of times people are using a scheduler like Slurm on premises, and then you can use Slurm on top of AWS. And there's not necessarily a lot of modifications that you need to do. Conceptually, it's still the same. You can submit your jobs, and then what you can do is once your jobs are finished processing, if you need to do like a visualization component, you can certainly do that on top of AWS. But then you start just refining this process as you move forward, as you start to get a little bit more used to it, as you determine how you want to tweak it. Maybe you notice that you can use a different instance type or something like that that might be more effective. Or maybe you tried it on a smaller scale with on demand just because that's how you want to do it first. And then now you're going to switch over in ParallelCluster. You might just add in the spot configuration. So now you're running on the spare capacity. And so really you start to kind of iterate through this loop as you're starting to move workloads inside of AWS. From a getting started standpoint, we do have resources available to you. So if you go to awsamazon.com/hpc/getting started, we actually have tutorials there that you can get started as well that are targeted specifically at HPC. So example, the first one would be just creating this elastic HPC cluster using AWS ParallelCluster, where it's basically a guide, a PDF document that you can download that walks you through all of the steps that you'll need to do just to start up. And so really it makes it pretty easy so that it tells you how to set up your users, how to set up permissions, how to install AWS ParallelCluster on your laptop, and then how to configure it so that it works with your AWS account, and then how to actually walk through the configuration file as well to give you a sample of what an environment might be. And then we also have other tutorials as well, like there's one for FSX, which is basically the managed Lustre service too. And so I really encourage people to go to this page to start looking at what resources are available just to help get started. Another nice benefit to AWS is that when you do get started, like when you do open up a new account, we have something that we call the free tier, where you can get a certain amount of resources with AWS free from that new account perspective. So you might be able to run like a very small instance just to launch, instance that you can get familiar with the platform, you can log in, you can see what it's like, just to start getting familiar with it before you're actually even charged for anything. Or you can work with, like I said, your account team. And if you can identify a POC, we might be able to work with you to get some credits that you can do to test something at scale as well. And so for example, like I said, here's the one on just deploying a cluster. It gives you a nice little overview. It shows you a diagram of what you're going to be setting up. kind of a picture architectural diagram to show you what resources are going to be used. And then there's actually a PDF, like I said, linked to it that walks through what you're doing and actually has a sample job inside of it as well. In this case, it's just running like a MPI Hello World job, but it shows you what steps you would take to create all of that for your environment. Another thing to talk about is we do have something called the Cloud Research Program. And so this is basically cloud credits for research. And so what this is a lot of times through this program, this is another method that you can use to get credits to prove out a concept of a larger workload that you want to run. And so this is something that you can submit online. However, I still highly recommend that you work with your account manager if you want to submit a credit request to the Cloud Research Program as well. But it's another resource out there for researchers. And then finally, another resource that you have that you can look at is as you start to use the platform, you can start to look at what we call well-architected for HPC. And so this is a white paper that's written, and it says it's basically walking through different concepts that we see and what we think are best practices for our customers. And so this is looking at your workload and how you architect your environment. And it's looking across like, how do you consider security? How are you optimizing for cost? How are you optimizing for performance? How is it more fault tolerant? Things of these concepts that you should think about when you're looking at a workload. And so it's a white paper that walks through what kind of questions you should be asking yourself as you're considering creating something on top of AWS. And with that, that's the content that I wanted to cover today. We have about 10 minutes left or so for questions. And so I'm happy to answer anything that's come up or talk through any kind of scenarios that people want to.
Thank you very much, Aaron. This was wonderful. And thank you for your time. Any questions from the audience? I have several myself, but I shouldn't be dominating the discussion. I think we have a quiet audience today. Before we finish, I would say that please, we have a, oh my goodness, my words are skipping me today. We have a follow-up survey for you to fill before the end, before leaving the webinar. Please do it because the feedback is important to us. But I have a couple of things to ask about, using the Amazon Web Services in general, because you pointed out a number of high performance and accelerated computing resources, which we make a lot of use of. So for example, one is the GPU-based resources, and we know how to use it. We have algorithms that are particularly developed for that. But the second thing that you pointed out were the FPGA resources.
Yes.
And how would the workflow work with an FPGA? Like if you want a class that has FPGAs on it, will you upload on the FPGAs the structures that you want them to have, and then on top of that, is it FPGA only, or will you be able to connect it with the HPC that uses the FPGAs to accelerate particular aspects of the problem?
Yeah, so at a high level, so when you're choosing like an FPGA, it's another instance that you launch, just like you would another instance that would have like FPGAs available to you inside of it. There's 3 different versions that we have currently, or 3 different sizes. So there's one where it has like the 2 extra large only has like 1 FPGA inside of it. Another one has 2 of them, and then finally the third size has 8 of them. But I'd be happy to connect you with additional resources on like what that process might look like, because we do have inside of our documentation, we do have kind of like what that workload or like what that workflow has for getting started with it, kind of like how do you launch it, how do you work with it, and things like that.
Okay. And the other question that I had is, I mean, I understand that the data storage and the instances that you have are of course decoupled. I mean, the instances died, and you have access to the to whatever data you generated and whatever output you created. I presume these are 2 completely separate accounts that you have that you need to couple at some level, right?
So just so I understand the question, and please correct me if for some reason I'm misunderstanding, it's that so your data, so it may live in different services. So like your data might be stored inside of like S3.
Yes.
And then you might be doing your compute, let's say on EC2. That is within the same AWS account.
Oh, I see.
So really, when you have an account, you have access to all of our services inside of that account, which is I think it's like 160 something right now.
Mm-hmm.
It's quite a large number, but you can choose what services you're using. And so inside of the same AWS account, you would be able to choose EC2 or S3 or Elastic Block Storage or something of that nature. And then inside of that account, all those services then are rolled up for a bill that you have. And then inside of the AWS account, that is something that you control. So you control who has access to it. You can create users inside of your account. So if you had like multiple people in your group that wanted to use the same AWS account, but that's contained all inside an AWS account. And then I think that might address like the account versus data thing and the compute. But then from an Amazon perspective, we don't look at your data. That's something that you own on top of the platform. So I think, was that also part of your question?
Yeah, no, exactly. And the storage and all the compute instances are interconnected in the sense that you don't need to have particular types of storage to access from particular types of compute instances.
No, what you would do is you would choose so those different storage services that I went through, you would choose what services you want to use for your solution. And so just having an EC2 instance, you'll be using Elastic Block Storage when you launch the instance. So that's kind of what that RIP drive would be on. And so that would be just kind of automatically, you would choose what size you would want for that, but that's just another component that would have. And then if you needed, let's say like a shared file system, you could have EFS, or you could have FSX for Lustre if you needed parallel file system, or you could just access the data directly in S3 if you wanted to follow a really common pattern. Of what people do is they store their data inside of S3, and when they launch their EC2 instance, they pull in the data that they need just through like a command line utility, do their processing, and then sync the data back to S3, and then deprovision all of their compute. But really all that's happening is happening inside of the same AWS account. You're just choosing where you want to run. So like what region you're going to be running in or something like that. So when you choose, so what I would recommend that you do is if you had like, let's say a large data set stored inside of Oregon, inside of our US West 2 region, I would then run your compute inside of US West 2 as well, so that you're running your EC2 instances inside of the same region that your data is, so that you're not transferring data across the country if you don't need to be.
I understand. Anything else? We had a very quiet audience today, which is fine. A lot of people will be watching it on our server afterwards. So I guess we are 55 minutes into the webinar, and I wanted to thank you, Aaron, for putting the time, and the presentation was really wonderful, and thanks everybody for attending.
Thank you. Thank you for having me. I appreciate it.
Absolutely.